A fully loaded airliner can weigh over 400 tons. Every time it lands, all that weight slams onto a narrow strip of pavement, thousands of times a year. Yet the runway doesn't crack, it doesn't collapse, and somehow it doesn't sink into the ground. But beneath that seemingly simple strip of concrete lies one of the most sophisticated engineering systems on Earth. A structure designed to control physics, soil, water, temperature, and even earthquakes. Tonight, we uncover the hidden science that keeps the world's airports from slowly disappearing into the earth. Consider one of aviation's giants. A Boeing 747 can weigh more than 800,000 pounds at takeoff. That weight doesn't rest evenly across the runway. It is concentrated onto a few sets of landing gear tires. At first glance, this seems like a disaster waiting to happen. But the key lies in one of the most fundamental relationships in physics. P equals F divided by A. Pressure is simply force divided by area. If the area increases, the pressure decreases. Aircraft engineers solve the weight problem by spreading the load across many wheels. A 747 has 18 landing gear tires, each one distributing the force over the runway surface. But even with this clever design, the pressure can still reach 200 pounds per square inch, which raises a surprising comparison. Here's something that seems almost impossible. A person wearing high heels can sometimes exert more ground pressure than a commercial jet. When a 100-pound person briefly balances on the narrow tip of a heel, the entire weight may be concentrated onto an area barely larger than a small coin. Because that contact area is so tiny, the pressure can exceed 1,000 pounds per square inch. That's several times higher than the pressure beneath many aircraft tires, which typically press against the runway at around 200 psi. Yet a jet weighing hundreds of tons can land safely without crushing the ground beneath it. Why? Because runways aren't just surfaces, they are deep structural systems. A runway is not just concrete. It is a multi-layered structure, sometimes more than 2.5 meters thick. Each layer performs a specific engineering role. At the top is the surface course, concrete or asphalt designed for friction and durability. Below that lies the base course. This layer of crushed stone acts as the structural backbone of the runway. Beneath it sits the sub-base, a thick layer of compacted aggregates that spreads the load deeper into the ground. And finally, everything rests on the subgrade, the natural soil beneath the airport. Each layer works together to spread the force of an aircraft into a widening cone. By the time that force reaches the soil, it is gentle enough for the earth to support. But none of this matters if the ground beneath the runway is weak. Soil is unpredictable. It can shift, compress, and collapse under repeated pressure. To prevent this, engineers transform the natural ground into a stable foundation. First comes mechanical compaction. Layers of soil are compressed using massive rollers until they reach precise density targets. Then comes proof rolling. Heavy vehicles drive across the site, revealing hidden weak spots. If the ground flexes or pumps, it is excavated and replaced. But sometimes compaction alone isn't enough, so engineers turn to chemistry. By mixing soil with lime, cement, or fly ash, soft clay can be transformed into a hardened foundation. Mud becomes rock. Modern runways also rely on geosynthetics. These are advanced polymer materials placed between soil layers. One of the most important is the geogrid, a lattice structure that locks aggregates into place. When stones interlock with the grid, they resist spreading under pressure. The result is a dramatically stronger foundation. Essentially, the runway becomes reinforced earth. Water is the greatest enemy of runway stability. When soil becomes saturated, it loses strength. Under heavy loads, trapped water can build pressure inside the ground. In extreme cases, the soil can behave like liquid. Engineers fight this with carefully designed drainage systems. Runways are built with subtle slopes. Water flows toward edge drains and underground pipes. Even the surface is grooved to channel water away from aircraft tires. Keeping the soil dry is critical to preventing long-term settlement. In the Arctic, the challenge is the opposite. Airports are built on permafrost, permanently frozen soil. If the ground warms, the ice melts, and the runway can collapse into mud. To prevent this, engineers install thermosiphons, passive refrigeration tubes buried in the ground. During winter, these devices pull heat from the soil and release it into the cold air. The result is a natural cooling system that keeps the ground frozen year-round. If you enjoyed this video, subscribe to Origin Lens for more hidden origin stories. And please watch the next video to discover the origin of shipping containers, the invention that quietly transformed global trade.